Okay, so we continue the discussion of this limit cycle, and in particular now what is the Hopf bifurcation. So we have to find fixed points. First we have a look at one fixed point of our system. There can be more. We linearize our system around the fixed point, as we know how to do it. We calculate all the eigenvalues of the Jacobian matrix. Okay, so if our system is n component, there will be n eigenvalues. For instance, here we put them on the plane. We have the plane real lambda and imaginary part of lambda. We know that our eigenvalues can be complex conjugated eventually. If they have a complex part, there must be a conjugated because the Jacobian matrix is a real one. Therefore, it has to be like this. So this shows, for instance, a particular example where eigenvalues are coming in complex conjugated. Here we have an isolated, so you count here, we have 7 eigenvalues. This could be an example of a 7-component system. Okay, if we have a 2-component system, there can be only 2 or 3 or more or so. So okay, and so this is the dimensionality of the system. So the Hopf bifurcation occurs if a pair of complex conjugated eigenvalue, this I'm talking about 0.3, have vanishing real part. Okay, and by changing the parameters of your system, as we know, these eigenvalues shift. Okay, and so the Hopf bifurcation is the point where a pair of complex conjugated gets vanishing real part, so their real part is 0, and by changing them, by changing other parameters in the system, for instance, you can shift them from a negative real part to a positive real part by crossing this Hopf bifurcation point. So the Hopf bifurcation theorem says that a small amplitude limit cycle emerges from the fixed point once you cross this bifurcation point. So for instance, the situation is depicted here when the pair of complex conjugated eigenvalues have real part smaller than 0, the limit cycle, there is no limit cycle, the system has a stable spiral as a fixed point, and this is shown in this example here. As soon as you cross the Hopf bifurcation point and the real part of this complex conjugated eigenvalue becomes positive, your stable spiral becomes an unstable spiral emerging from the fixed point, and you will have typically a limit cycle, a small limit cycle emerging that grows, okay, around the Hopf bifurcation point. Okay, so this Hopf bifurcation theorem only holds in the vicinity of the limit cycle. It doesn't say anything about what happens when you are sufficiently far away, from this Hopf in the vicinity of the Hopf bifurcation point. Okay, so it doesn't say anything what happens when you have a large real positive real part. Okay, but this is a typical situations we are looking at. So we look whether we find pair of complex conjugated eigenvalues, okay, and whether under which circumstances they have real part equal to 0. And of course we can have many eigenvalues, and typically the most interesting situation for us, and it's that all the other eigenvalues have negative real part. It means that they correspond to stable directions. Okay, in particularly if we look at 2-component system, what does this Hopf bifurcation corresponds to? It's found precisely when, well, you know that the sum of eigenvalues, the eigenvalues have negative real part and they are complex conjugated. This means that the Jacobian matrix A has a positive determinant at trace equal to 0. Okay, so this is the Hopf bifurcation point. Trace is 0. The trace is the sum of eigenvalues, because these are purely imaginary and complex conjugated. The sum is 0. So in a 2-component system, and only in 2-component, where we know the structure of our fixed point by plotting determinant of Jacobian and trace of the Jacobian, the Hopf bifurcation point is precisely here on the positive positive axis, say positive horizontal axis. All right, we continue the discussion of limit cycles for two-component system. For a two-component system, we know that we can fully characterize the nature of the fixed points by plotting the trace and determinant of the Jacobian matrix. In particular, the Hopf bifurcation point is here, is where the determinant is positive and the trace is equal to 0. This is the Hopf bifurcation point, and this point is at the boundary between a solution which is a stable spiral to an unstable spiral. Okay, right. So the trace of the matrix, of the Jacobian matrix, is has to be equal to 0, and we are asking, okay, what is the sign pattern that gives rise to 0 trace? To get the 0 trace, I must have, in general, that the two diagonal elements, one is positive and the other one is negative. All right, they could go to 0 simultaneously at this point, but this is a very special case. Normally here and here you have two different terms. Okay, there isn't, unless there is a special symmetry. In the most generic case, these two terms will be different. Therefore, one has to be positive and the other has to be negative to give 0. So if we find that our matrix, Jacobian matrix, has minus and minus here, for sure we can conclude there is no Hopf bifurcation in this system. And the minus term is a typical one that we find in our systems, because our system typically describes some type of chemical reactions where our concentrations evolve in times. There is always some degradation here. This degradation gives a negative contribution to the to this diagonal part of the Jacobian. Therefore, to get the positive term in there, one must have that the derivative of this h has to be such that the element 1, 1, 1 of this matrix, which is given by derivative of h minus alpha, has to be positive. So the h must be sufficiently large and positive for this to happen. And yeah, the way I write this one, I mean that there is a degradation term and there is a synthesis term. The synthesis term is typically positive and describes what are the reactions that are increasing the the number of particles and so on. All right, so so this is the sign pattern to have trace of a equal to 0. And what happens to the other two terms, to the off diagonal terms? So we always have required that the determinant of a has to be positive. So our Hopf bifurcation is here. So this sign pattern gives a negative contribution to the determinant, because the determinant is given by the product of these two. So this is a negative contribution. Therefore, I have to have a sufficiently strong and positive contribution to the determinant coming from the other two sides. Okay, so this happens. For this to happen, I must have also a specific sign pattern. I must have opposite signs in these two off-diagonal sides, such that I get a positive determinant. Okay, the product of these two must be compensated by a sufficiently positive term coming from this. Okay, and therefore there are only two sign patterns that comes, so I can complete the sign patterns of my matrix in the following way. So if I have a plus sign here, I must have a minus sign, or if I have a minus sign here, I must have a plus sign here. This is called a substrate depletion sign pattern, and this is called the activator inhibitor sign pattern. And the reason for this will become clear a bit later. Okay, so there are two signs pattern. Of course, I could also swap the signs here and have a minus sign to a plus sign here. Then the things will be slightly different. The role of plus and minus can be swapped. For instance, I can swap the two rows or the two columns. So there are other type of matrices, but they are all obtained from these two by symmetry. Okay, transformation. So it's very important to recognize that for two component systems there are only these two type of sign patterns for the Jacobian that can give rise to an Hopf bifurcation. First of all, this is a necessary condition, right? I still have to have the values are such that they give trace equal to 0, right? And I need to have this off-diagonal component sufficiently large such that I get positive determinant, right? So this is we understand that these sign patterns are a necessary condition, but they are very useful, because if I have a system where I don't find these sign patterns, then I can already conclude in that system there is no Hopf bifurcation. Okay, and so it's very important to realize that this plus, it's what is called autocatalysis, to have a plus sign here. It means that the increase of the concentration of X increases the rate of production of X. So X must be here to have the plus sign in the diagonal. X must be such that increases its own, when increases also the rate of its production. This is why it's called autocatalysis. So somehow it's a variable that reinforces itself. All right, we continue now with one specific example. This is called the Selkov model. And this is described by these two differential equation, x dot and y dot. These are some chemicals, and these are some chemical reactions. They describe some chemical reactions, okay? So these chemicals are having concentration x and y are the concentrations. Therefore, they have to be larger than 0, either eventually 0. Okay, so we have learned here that that only some specific sign patterns can give rise to Hopf bifurcation. So we go directly to the calculation of Jacobian. Now, normally we have to look at the Jacobian at the specific fixed point, but we can do straight here the calculation of the Jacobian for a given point x and y and look at it. Okay, so in the first element is the derivative of this with respect of x. Okay, this gives rise to 2 times xy minus 1. Okay, and the derivative with so the derivative of x of this 2xy and minus 1 comes from this. Okay, the other term is the derivative of the same first row with respect of y, and this is a plus x squared. And then we continue, okay, right? The derivative with respect of x and the derivative with respect of y of this quantity. All right, this is our a, the Jacobian. Okay, now we can think about and analyze the sign. First of all, x and y in this model are larger than 0. Therefore, well, this element is certainly negative, always. This element is positive, this element is negative. Therefore, I have this, this sign. And here I see that if x times y is larger than 1/2, then I get this possible substrate depletion oscillator. So this is the sign pattern that I get from this case. I have to check still whether it's realized. If I don't see that, for instance, in a model that this sign pattern is not realized, then I can already stop. I can already conclude there is no possible Hopf bifurcation. Here, what is crucial, 2xy, you see this is the term, there is a minus 1, this is the term that can give rise to this plus sign. All right, and where is this coming from? It's coming from exactly from this term. This term is an autocatalytic term, right? Because you see x dot grows if x grows to this term. Of course, there is also the degradation. The degradation increases as x increases in concentration, but this grows as x squared. This grows as x, so there are possibilities here to get a plus sign if x squared times y is sufficiently large, such that this one is larger than the contribution of degradation. Right here you see on the other diagonal term we only have contribution from degradation type of terms. All right, so that's there is nothing here that can happen. It always stays a minus sign. All right, so this is a very quick and simple analysis that we can already do. So this has a potential of becoming a Hopf bifurcation. And now we have to do further work to see whether this is really happening. Okay, so what is the further work? Actually calculate where is the fixed point. Fixed point, first of all, you remember the definition of null clients are the sets of points where this is vanishing. Okay, so it's simple calculation show that this vanishes when y is equal to this, and this term, the right hand side, vanishes when y is equal to this other quantity. Okay, so the fixed point is the intersections between these two, which is very easily found. It has to be x equal to b and y is equal to b divided by a plus b squared. Okay, so this is our fixed point. So it's very interesting to plot the null cline. So in this setup, now I'm considering a fixed. All right, I keep a fixed, whereas I let b vary. Okay, so I plot these two. I plot the first one as a blue line here. Okay, so when x is equal to 0, the first null cline is 0. Then it grows and has a maximum and it goes to 0. The other one is a decreasing function of x, okay, which I plotted here. And as I used as the only, I have two parameters here, but I keep a fixed and I let b vary. Okay, so if b is small, you see that this this second null cline has this shape, so it has an intersection here. Let's consider this and call it case 1. Okay, as b grows and increases, okay, and it goes up, so this intercept is also increasing. This intercept is proportional to b, this this begin point, so it's increasing, and now the intersections is further at larger x. Okay, this intersection is takes place as at the point x is equal to b. So as I increase b, then I go to the situation 2, and there is always an intersection, because the first null line decays as for large x as 1 over x, but the second decays as 1 over x squared. So the dashed line decays faster at large x, so there is always intersecting in one point. Okay, and this is the only point. This is our fixed point. So this fixed point moves as I change b from this point further up and here. Okay, so, and I have to see here, okay, so where is the Hopf bifurcation taking place? Okay, so we have a system. Now our system, let's write it a bit in a more general form. I have x dot is a function f of x and y. Y dot is a function g of x, y. Okay, so let's have a look at case 1. Actually, it turns out that just by the geometry of how these two null cline intersect, so you see that the topology of the intersection changes, right? So the intersection of the blue and the dashed red null clines here is such that the blue climbs up like this. It has is a curve with a positive derivative, and the other one is going like this. This is the dashed line. So I'm just looking now at the case 1, right? We can generalize and have a look at the case 2 later, but okay, let's go deeper into this case 1. The case 2 follows easily. Okay, so what do I have in case 1? I have the first curve. The first curve is f. F is this one. F is equal to 0. So the set of points in this f, in these blue curves, are all points where the null cline, so this f is equal to 0. Okay, and this null cline separates two regions. To the right side, we have a region. If I do the analysis, you see the region where x is large and y is small. Its f is smaller than 0, and this side of this blue line is where f is larger than 0. And the same way, I trace the set of points as a dashed line where g is equal to 0. G is this term. And above this, I have a region where g is smaller than 0. Okay, this is the region where x and y are large, so this term dominates. Whereas the region below the curve is the region where g is larger than 0. Okay, so this is sufficient now because I can calculate the derivative of the Jacobian as this fixed point. Okay, at this fixed point, I have my f, okay, equal to 0, and then I want to calculate at this point the derivative with respect of x. So I'm looking at infinitesimally neighboring point here, okay, and I'm looking where, where is this, okay, so I'm looking at the local difference between f here in infinitesimally close and f where it's 0. Okay, so if I move to this point, f is smaller than 0. Okay, so the difference, this derivative with respect of x of f at this point is negative. Okay, and with the same type of reasoning, when I differentiate with respect of y, I'm looking at the difference between this point and this point. And this point f is positive, in this point f is equal to 0. Okay, so this derivative of f with respect of y is larger than 0. And likewise, I can do the calculation for the derivative of respect of g of x and y. Okay, so one has to be a bit careful now. I wrote this in this form. This first element is the derivative of x with respect of f. Sorry, the derivative of f with respect of x. So this first element is negative according to my calculation. This element is this one, is the derivative of f with respect of y. This is positive according to my calculation. And these two, I found out that these are both negative. Therefore, what I conclude in this case, one, just the topology of the intersection gives me this sign pattern. This sign pattern is a sign pattern which is not compatible with the Hopf bifurcation, right? We have minus, minus, plus and minus. This can never give a 0 trace, right? Because I have minus in both signs. So I conclude that this topology is not a good one. The Hopf bifurcation will never take place when the fixed point is in this part here, right? When the intersection is like this. In case 2, I have a different type of intersections, and I can show, and I leave this as an exercise, that when the topology is like this, such that you see in this case 2, what changes is the curve for f, right? The g comes down with this negative derivative, and the f is also coming down with the same negative derivative. Okay, so there I can show that in that case I get a sign pattern compatible with a substrate depletion. So therefore, if there is a Hopf bifurcation, it will be only in this part where this dashed line has gone above the maximum and is intersecting the other curve, the blue curve, with the same derivative. All right, we continue with this Selkov model. So what we found was the following. If we plot the two null lines, one is dependent only on the parameter a and the other one on a and b, and we keep a fixed and we change b. By increasing b, the null line, the dashed one, moves, and the intersection moves from this side of the maximum to the other side of the maximum. Okay, we concluded that in this first region up to the maximum there cannot be a Hopf bifurcation, and if Hopf bifurcation takes place is somewhere here. All right, now we have actually to do the calculation and to find it, right? So we do it, we again calculate the Jacobian, we have it here rewritten, and by doing a simple calculation we find immediately that the determinant is a plus x squared, always larger than 0, so there is nothing to search for here. Then we have to require that the trace is equal to 0. The trace is the sum of these two terms. Now here, instead of x and y, the generic value, we substitute the coordinate of the fixed point, which are here on top. X is equal to b, and y is b divided by a plus b squared. Okay, replace these two values here, you find some equation. The equation is given here, and you want this to be equal to 0. Okay, so you have to find the set of points b and a such that this is satisfied. The solution is shown here. It's a simple problem to look at. So you plot on the plane of the parameters a and b. Okay, you find the following. So you find the region of points where a and b are such that the trace is 0 is given by this solid line, and the solid line separates a region where the trace is negative and another region where the trace is positive. Okay, so you see there is a threshold of a when this Hopf bifurcation takes place in a region where a is smaller than 1/8. So if a is larger than that, no matter what the value of b, you're always in a trace region where the trace is smaller than 0. Okay, so given now a fixed value of a smaller than 1/8, you take here, you move along this line and you find 2 points where b where the trace is equal to 0. So there are actually 2 Hopf bifurcation points for fixed a. One is when b is alpha, and the other one is when b is equal to this value beta, alpha and beta. Okay, I fixed a and I move along this one and I cross this line, trace is equal to 0 in these 2 points. All right, so therefore in this graph I write again alpha and beta. These are 2 points where I have a Hopf bifurcation. So when I change b and I increase, so no Hopf bifurcation possible here. Here is the possible Hopf bifurcation, and actually takes place one here in this point and one here in the second point. So there are 2 Hopf bifurcation in this model, and the Hopf bifurcation theorem says that in the vicinity of this Hopf bifurcation there will be a limit cycle. Okay, and in the unstable region, so where the trace here is positive, okay, that's my fixed point changes of nature. Here the trace of a is positive all over here, here. The trace is 0 exactly at this point. The trace becomes, sorry, my mistake. So in this part of the graph, the trace of the Jacobian is positive, is negative all over here up to this point. At this point it becomes 0, Hopf bifurcation. Then the trace becomes positive here, instabilities. So the fixed point becomes an unstable spiral here, and another Hopf bifurcation here. So what happens in practice is the following here. Is shown here. So when the null line intersects in the region between alpha and beta here, at around this fixed point, you will have a limit cycle. This fixed point is an unstable spiral, you will have a limit cycle. So you start seeing a limit cycle when your b is such that you're crossing this point. There will be a very small limit cycle around here. The limit cycle grows in the middle here, and it becomes smaller again here. So there is a nice animation of this Hopf bifurcation in Wikipedia. There is an animation file where it shows what happens when you're changing the b such that this dashed line moves from intersection here, having an intersection in this region, moves further away.